Reservations in two-way slabs by means of yield lines. This video will deal with cases 21 to 25, and it's about a rectangular concrete slab with fixed ends on the four sides. It will handle in particular case 23, which is about an edge square hole. We draw the yield lines with the 30, 45, 60 rule, and we indicate the reservation with size D1 on a distance D4 from the left-hand side of the slab. This is a two-way slab, so E must be between A and 2A. The square reservation, so D2 is equal to D1. It's at the edge. It means that here the D3 is 0. And we said that we look at the reservation between the two yield lines, so not cutting the yield lines. So that means that D4 is situated between this and this. You can now fill in the values of S1 and so on, and then you will see that the yield line, that the reservation must be between the yield lines so that you have a simple condition on it. It goes from the left to the middle and to the right. So on the left-hand side, you see that the limit is D1 because this is 45 degrees. So this is D1, the distance. And on the right-hand side, of course, this is D1 too, but you have this D1 and this D1, so you have D minus 2 D1. So those are the two limits of this reservation. We will now calculate the work done by the external forces. We look at the orange colored elements. It consists out of rectangulars. So the mean deflection is delta over 2. And then the total load is, of course, B, that's total B, minus S3 minus S1 times A. But we have too much because we have to subtract the reservation, which is D1 times D1. And the mean deflection is, of course, D1, or the maximum deflection, sorry, is D1 divided by S4. That's for this point. Then we go to the triangles, the green area. The green area is A times S1 and A times S3, and the mean deflection is delta over 3. We use dimensionless parameters, and we arrive at this equation. The work done by the internal forces is this yield line B projected on this axis of rotation. So it is B minus, of course, where the reservation is, minus D1, multiplied by the angle of rotation, which is delta over S4. That's this part. Then we have this yield line projected to this side. It's B over S4. And then we have on the right-hand side A divided by S3. And this is also A divided by S3. We have here A divided by S1, and this A is also divided by S1, so that's where the 2 is coming from. And then at the bottom, we have B divided by S2 and B divided by S2. Now we can put E equal to D, and we can we can calculate M, which is a function of alpha and alpha 1, and it looks like that. First thing we notice is that this formula is independent of D4. So you must take care of it, that you must still fulfill the condition on D4, but it's not appearing in the formula. Let's give an example. You have a square slab with 20 centimeters depth, 40 millimeters concrete cover, floor finish of 2, and a mobile load of 20. And there is a reservation in it of 1.5 by 1.5 meter. So what is the reinforcement needed in this slab? We calculate the load in ULS, which is 1.35 times the permanent load plus 1.5 times the mobile load. It gives you 39.45 kilonewton per square meter. These are the different parameters. Alpha is then B over A is 1 and alpha 1 is 0.3. We can calculate the maximum bending moment. It's 19.6 kilonewton meter per meter. We convert that into reinforcement. For that, we calculate the lever arm in X and Y direction, and we take the mean lever arm, which is 152 millimeters. Then we calculate the needed reinforcement, which is 1.1 times the maximum bending moment, divided by the lever arm and the yield strength of the reinforcement. Gives you 362 square millimeter per meter, or it's a diameter 8 every 139 millimeter. This is a very strange number. We will not use that in practice. We will round it off to 8 diameters 8 per meter, or you can choose a bigger diameter. Then you fill in here the bigger diameter, then you will arrive at a lever arm of 150. You recalculate the needed reinforcement. It's 367. So you can also use diameter 10, 5 per meter. Let's do a second example. It's an existing slab. The only thing you know is that it's reinforced in two directions. You don't know the load that it was calculated for, nor the exact amount of reinforcement. They want to make a reservation in the slab of 2 by 2 meters at 2-meter distance from the left-hand side. The question is this possible? Can we do that? We calculate the different parameters. Alpha is B over A is 2, and alpha 1 is D1 over alpha over A, which is 0.4. So now we can calculate the maximum bending moment without the hole, which is M0 divided by Q, the load, because we do not know the load. Right-hand side is now only a function of the geometrics of the example. And we arrive at 0.868. Then we can calculate the maximum bending moment with the hole. And we can calculate it, and we have then 0.829. This means that 100 times M0 over M, or the bearing capacity, is 105. So this means that we can make this reservation without losing any bearing capacity. So bearing capacity is defined as 100 times maximum bending moment without the hole divided by the maximum bending moment with the hole. This is how we can formulate it. We use dimensionless parameters, and we know that case 23 type of reservations must fulfill this condition. So alpha 4 must be between those two limits. And the bearing capacity, when we use the formulas of the previous slides, you can calculate this equal to what is stated on the slide. Now we can put on the x-axis alpha 1, which is between 0 and 0.5, and on the y-axis is the bearing capacity. We do that for alpha equal 1, 1.5, and 2. And you will see that we have 3 curves, and every situation is situated between the 2 curves. But now what happens with the condition alpha 4? It must be between 2 limits, but the upper limit is a function of alpha. So the first, what we notice is that alpha 4 must be between alpha 1 and alpha minus 2 alpha 1. So alpha 1 has a limit of 0.5, so that we have to obey. So it's the minimum of 0.5, but when you make this equal to that, then the minimum is also alpha over 3. So you have to take the minimum of 0.5 and alpha over 3. To give you an example, for instance, for alpha equals 1.5 and alpha 1.3 is this blue curve, and alpha 1 must be smaller than 0.5 as this side here, or 1.5 divided by 3, so it's also 0.5. So that is the blue dotted line. The blue dotted line, it gives you the upper limit of uh, of of alpha, of the upper limit of alpha 1. So it stops there. When we take alpha equals to 1, then you will see that this dotted line is here, and that the value of this curve is not right. It should be hidden. It's not there, because this is the only point. This and left of this point is the only point that is valid. In the previous example of alpha equals 1.5, you can visualize it like it is like that, and this is going from left to the right. You see also, this is an interesting point, that for alpha 1.5, its 100% bearing capacity is at this value of 2.42. It means that for every value bigger than 2.24, there is no loss in bearing capacity. And for the others, let's investigate it in a little bit in more detail. This is the same graph as previous one. We are interested in this value. When you blow it up, then you will see from alpha from 1 to 2 that from this range here, you have a loss of bearing capacity. But this loss is less than 1%. In all cases, it's less than 1%. So there's no significant loss at all. So it means that there is no loss when the reservation is larger than more or less 1.25, so 1/4 of the smallest size of the slab. Square roll at the edge of a rectangular concrete slab type 23 has in fact no significant loss of bearing capacity as long as the yield lines are not crossed. So these are different possibilities of reservations. All those possibilities shows that you do not have any loss of bearing capacity. You have a little bit because there's a yield line, a negative yield line that is cut on this side, on the top side. So that's why you have sometimes bearing capacity loss of less than 1%. So, but this does not count.